Today, we're diving into a pretty amazing discovery that could seriously boost the future of clean cars. And the wild part? It all boils down to finding one single, absolutely perfect measurement. I know, it sounds a little too simple to be true, right? But you're about to see how researchers found that one tiny, almost invisible design choice can have a massive, and I mean a massive, impact on the power and efficiency of the cars of tomorrow. So, to really get why this little detail is such a big deal, we gotta pull back and look at the big picture. The enormous challenge of cleaning up the way we get around. The scale of this problem is just staggering. A full quarter, 1/4 of all the energy we use on this planet goes into moving us and all our stuff. And that heavy reliance on fossil fuels, well, it's a huge driver of greenhouse gas emissions. This is exactly why we need a new plan. And one of the most exciting options out there are fuel cell vehicles, or FCVs. The amazing thing about them is that unlike the cars we're used to, their only byproducts are heat and plain old water. It's an incredibly clean way to drive. And the potential impact here isn't just a small tweak. It's huge. One study figured out that if we replaced all the light-duty vehicles in the US with FCVs, we could slash greenhouse gas emissions by 44% and basically eliminate our need for oil for those cars. That is a total game changer. So how do these super clean engines actually work? To really get this breakthrough, we've got to pop the hood of an FCV and take a look at its heart, the fuel cell itself. Okay, we're talking about a specific type here called a proton exchange membrane fuel cell. Let's just call it a PEM fuel cell. They are perfect for cars because they run at pretty low temperatures, they start up quick, they're small, they're light, and they're super efficient. But there's always a but. They've had challenges with cost and performance. And when you dig into that cost and performance puzzle, you find one component right at the center of it all, the bipolar plate. You can think of it as the backbone of the fuel cell. It handles everything from making sure electricity flows to delivering the fuel. Now this is where it gets kind of wild. This single part, the bipolar plate, can make up nearly half the cost of the entire fuel cell. And get this, it's over 70% of its weight. So it's pretty clear, right? If you can make this one part better, cheaper, and lighter, you change everything. Okay, so we found our target, the single most important component. Now let's zoom in even closer on the very specific engineering puzzle that these researchers were trying to crack. If you could look at the surface of this bipolar plate, you'd see these tiny little grooves. There's the open part, called the channel, that acts like a tiny highway for the hydrogen and oxygen. And then there's the solid part, the rib, that actually conducts the electricity that the fuel cell is creating. So here's the billion-dollar question. What's the absolute perfect balance between that solid rib and that open channel? This relationship is what they call the rib-to-channel ratio. You see, if you make the channel too wide, you might not get good electrical conduction. But if you make the rib too wide, you could end up starving the fuel cell of gas. Now, to solve this puzzle, the researchers didn't just take a guess. Nope. They ran incredibly detailed computer simulations on 16 different designs, carefully tweaking that rib-to-channel ratio from one extreme to the other, just to see what would happen. And this is where it gets really, really cool. Through all of that meticulous testing, they weren't just looking for a pretty good design. They were hunting for the perfect one, the just right Goldilocks ratio. All right, the moment of truth. After simulating all 16 of those different versions, what did they find? Which one delivered the most power? The result couldn't have been clearer. You could literally see it in the data. When the ratio was too low, performance was meh. As they increased it, the performance shot up and up until it hit a perfect peak. And then, as they kept increasing it, the performance started to drop right back off again. It was a perfect Goldilocks curve. And that peak performance, it wasn't just a little bump. At that sweet spot, the fuel cell kicked out a staggering 57.3% more power compared to the worst design. That is a massive leap forward from just a simple change in geometry. But why? Why does this happen? Well, it all comes down to traffic flow for the gas. When the channels are too wide, the gas just goes straight down. But when they're just right, something magical happens. The gas not only flows down, but it also mixes sideways under the rib, feeding the whole system way more effectively. And if you make the channels too narrow, you get a traffic jam. The fuel can't get in, and the water that's created can't get out. Okay, so we've been deep in the weeds of engineering here. A tiny ratio makes a fuel cell way more powerful. But let's pull all the way back out. What does this discovery actually mean for the real world, for us? It's like a domino effect of good news. This one little optimization means you get more power from the exact same amount of material. That means higher efficiency and less wasted fuel. It even means you can start using newer, cheaper materials for these plates. And all of that together, it makes fuel cell vehicles cheaper and better, which helps speed up the entire shift to cleaner transportation. And it really just makes you think, doesn't it? This huge leap forward didn't come from some brand new miracle material. It came from obsessively perfecting one tiny little measurement. It leaves you with this really fascinating thought. How many other massive breakthroughs are just hiding in plain sight, waiting for us to pay attention to the small stuff? Thanks for digging into this with us.